is also called Burnside's lemma. It's also called Cauchy-Frobenius Burnside lemma. Okay, here is the theorem. So let me state it. Theorem. So let's put it in a different color. So it's highlighted. So here is the theorem. Okay, let's see. Let G be a finite group acting on a finite set X. Then the number of orbits equals, so the number of orbits here, of course, means the number of G orbits for the action of G on this set X equals, and here is the formula, and it's a beautiful formula, 1 over the order of G. It's a finite group, so this makes sense. I sum over all elements of G of the cardinalities of X upper G, okay, where X upper G, recall, is, this is the definition, all those X in X such that Gx equal to X. So this makes sense when you are given an element G of G, and here we are summing over all elements of G of G. So here that element is given to me. So I compute this. So this is a very beautiful formula. It says the following. So here it has the following interpretation. This is the average number of, see, X upper G is all those points of X that are fixed by this group element G. And so what you're doing is taking the average number of fixed points. So the right-hand side can be interpreted as the average number of fixed points. So it has the interpretation, number of orbits equals the average number of fixed points. That's a very nice statement, I think. I hope you will dwell on this to appreciate the beauty of this statement. Okay, so before proving this, let us apply it. So let's apply it. Application to the necklace problem. So recall the necklace problem that we started out with. We wanted to solve this problem, and now I claim we can solve it by applying this lemma or theorem, as I've called it. Okay, so this is what I mean by the orbit counting lemma. So I'm sometimes calling it theorem, sometimes calling it lemma. It doesn't matter. Okay, so this is what is meant by the orbit counting lemma. It's called so because the left-hand side of it is the number of orbits. Okay, it gives a formula for the number of orbits. Okay, so let us recall what our problem was. So you're given I hope you remember the problem. So we are given beads of two colors. Beads of two colors. And the question is, how many different necklaces. So let's say these colors are red and blue and red. You can choose any two colors. We had chosen blue and red. How many different necklaces with n beads can you make? Where n equals 1, 2, 3, etc. N can take any value. And for each of these values, we want to count the number of necklaces. Okay, so we had done for some small numbers, 3, 4, 5, etc. And we had I had assigned as homework for 7 and 8. The answer, if I may remind you, here is 18, here it is 30. And if you go all the way to 20, the answer, let me look it up, what the number is. The number is 27,012. Okay, that's a very large number. Okay, surely while you may be able to do it for 7 and 8, you can enumerate and do it. Doing for 20 beats by brute force seems quite a formidable task. And how are we sure, even if we should be able to enumerate so many of them, let's say we enumerated 20,000, 27,000 of them, how are we sure that we have enumerated all of them? So we want some kind of theoretical way of counting without actually enumerating. And I'm claiming that this orbit counting lemma will help us do precisely that. Okay, let's see how to apply this. Okay, so let's do it with n equal to 8. Okay, so I want this answer 30. So I'm going to get that using the orbit counting lemma. Okay. So recall the following. How does the orbit counting lemma apply to the necklace problem? So we had already seen this, and even in the first lecture. And recall that the group D8, the dihedral group of order 16, which we call D8, which is the symmetries of the octagon, regular octagon, right? So this has 16 elements, namely 8 rotations and 8 reflections. So we had discussed this group in some detail. So D8 acts on diagrams. So what do we mean by diagrams? It means that you draw pictures like this. So I'm not formally writing down the definition of a diagram, but I'm telling you what it is. Okay, so you have these vertices of the octagon. You can fix this picture. Okay, and a diagram means that at every position you place a bead, either blue, it could be either blue or it could be red. Okay, so at each of these positions, I place a bead. And there are two choices. It could either be a red bead or a blue bead. Remember, the beads are all identical. You can't distinguish between red beads. You can't distinguish between blue beads. And let's even say that between blue beads and red beads, you cannot distinguish them except for the color. Okay, so all these are identical beads, except for I can distinguish if a blue bead from a red bead, but between two red beads and between two blue beads, I cannot distinguish. Okay. So how many diagrams are there? So this is my G. This is going to be my X. Okay. And how is it going to act? Well, it's going to act. We have seen this also. So let me draw a particular. So let's say I put red bead here, red bead here. Here, this is just arbitrary. and blue beads at the remaining places. So this is an example of a diagram. Okay. And if I act the 45-degree, so let's say I take an element of G, it is a reflection, one of the 8 reflections, or it is one of the rotations. So for example, if I choose the 45-degree rotation from G, how does it act on this diagram? It will turn, let's say if it is called clockwise, anti-clockwise, it'll turn everything in this direction. So let me actually write it down what the image will be. So I have the string and I have these positions, and this red bead will move here. So this becomes red, this will move here, this will move here. Everything will be shifted by 45 degrees. Okay, and the rest are blue. So this moves here, this blue will come here, so I write it here, this blue will move here, and this blue will move here. Okay, so this is under 45-degree rotation clockwise, anti-clockwise. Similarly, you have, for example, if I take a reflection, if I reflect along this, say, axis of this line, then these two will get interchanged. The red will go here, the blue will come here. These two also will get interchanged. This will become red and this will become red and this will become blue. These two will get interchanged, but it won't make a difference because both are already blue, and this red stays red and this red stays red. So it is clear, I hope, how the elements of G act on diagrams. And what we had observed was, if we get a different diagram, like so, for example, here, these two are definitely different diagrams, but because a diagram is what I see. So this looks different from this, because here, right here, this position is blue and this is red, right? These are different as diagrams, but they are the same necklace. Okay, what we had decided was number of necklaces. So here is the observation that I'll recall for you. Number of necklaces. This, we had done it even in the first lecture. Number of necklaces equals number of orbits of D8 on diagrams. And so if I am set for the application of the orbit counting lemma, because I have already observed that this is the number of orbits, right? So now I have to just count the orbits. So let me pause here and ask if you have any questions. We are now going to apply the orbit counting lemma to solve this problem. So this is like a climax of our, if you imagine that the lecture to be a movie, or the set of lectures to be a movie, then we are nearing the climax of the movie, and I hope you're excited by it. So let me pause and ask if you have any questions. Does this make sense? So here is our lemma. We are going to apply it to this situation. Any comments? Okay, if not, I'll continue. Feel free to interrupt me at any point and ask if something is not clear. Okay, so let us start. So number of orbits, therefore number of necklaces, equal to number of orbits. But what is the number of orbits? What should I write here? So the formula is, let me write it here. this is the right-hand side of the formula. So I'm going to write it. So 1 over the order of the group. So it's 1 over the order of D8. G is D8 here. So 16. Okay. Now here comes the calculation. So for each element of the group, I have to find out how many diagrams, this X is the set of diagrams. How many diagrams are fixed by G? That is, if I apply G, it won't affect the diagram. So for example, if I take first element to take would be the identity element. It's natural that we want to consider that first. So please tell me how many diagrams are fixed by the identity element. I need your help here because I can just do this calculation in half a minute, but if I do it that way, I'm afraid I'll lose you. So please help me and speak up so that all of us are on the ball, so to speak. That is, we are following what is happening. So the question is, how many diagrams are fixed by the identity element? So what is your answer to that? So how many diagrams are there? What is the size of this set X?
2 power 8.
2 power 8. Very good. Okay. And so let's write this. I'll use this color here. The cardinality of X is 2 power 8. Very good. Very good. So here is, for example, one diagram. Here is another diagram. Now, does this remain fixed under the identity? What does the identity mean? I do nothing to it, right? So it naturally gets fixed. So what should I write here? What is, if G is the identity? Yes, please.
2 power 8.
Very good. 2 power 8. Very good. Okay. So the first number is the number of diagrams fixed by the identity. Okay. Now let's go to suppose I take the rotation by 45 degrees. Right. How many diagrams are fixed by, now it becomes interesting. How many diagrams are fixed by such a. So what it means is, I hope you understand. You imagine a diagram and turn it by 45 degrees, and the diagram should look the same. How many diagrams are there? So any answers? So imagine putting some colors on these vertices, but the condition is that if I turn it by 45 degrees, the diagram should look the same. Yes, madam, I didn't hear you properly.
Full red and full blue.
Full red or full blue. Very good. If I put blue everywhere, right? If all beads are blue, no matter how I turn it, it's going to be fixed. If I turn by 45 degrees, it's going to remain fixed. If all are red, surely that is also going to get fixed. So there are two of them. Are there any more?
Consecutive colors are same.
So consecutive colors are same, meaning this is the same as this, but these two are consecutive. So this is the same as this. So this is the same as this. Correct. What does consecutive colors are same mean? It means this is the same as this. This is the same as this. Therefore, all three are the same. But this is the same as this because it's consecutive to this. So what do I conclude? This is the same as 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 this is the same as, and so on. So either all are red or all are blue. There is nothing else. So you can think another way. If this is blue, so somewhere, suppose consecutive colors are not the same. Here blue and here red. Clearly, when I move this when I move this by 45 degrees, this blue will come here. And so it is not fixed by the 45-degree rotation. So if two colors are different anywhere, say these two are different or these two are different anywhere, you will get a contradiction to the fixed. Such a diagram will not be fixed by the 45-degree notation. So will you all agree that I write 2 here for that? So that is for the 45-degree rotation. Okay. Now, this is for 45-degree rotation clockwise. Let us take 45-degree, sorry, anti-clockwise. Let's take 45-degree clockwise. Then what is your answer? Instead of turning this way, I'm turning this way.
2.
2, very good. It's the same logic. Okay. How about 90-degree rotation? Anti-clockwise first. So whatever is here, this goes here. So these two must be the same color. And this goes here. So these two must be the same color. This goes here. So these two must be the same color. So all these 4 are the same color. And these 4 are the same color. Okay. So can you tell me the answer, please? So let's do 90-degree, the other rotation also. I'm waiting for you to answer.
Or
4, very good. Correct answer. Why, madam? Can you explain? Very good. That's the correct answer.
red, blue alternatively.
Hmm.
There are 2 choices.
Hmm.
And all red, all blue.
Very good. That's it. So, indeed, that's correct. But another way to think about it is here, all these are the same color. But these 4 colors could either be, I have drawn them in green, but that green could all be, we don't have green beads. We have either blue or red beads. So these 4 could all be red or all be blue. So that's 2 choices for that. And these 4, independently, there are 2 choices. They can all be red or they can all be blue. Or, as she explained, you can think either it's all red or all blue or blue and red alternating. Right? So blue and red alternating with starting here, blue is different from starting here is red is counted different because we are counting diagrams. So if I put blue here, red here and so on, alternating, that is different from the diagram if I start with red here, blue here and so on. Right? They are the same as a necklace, but they would be different as diagrams. And remember, we are counting diagrams here. X to the G, X is the set of diagrams. So this is 4. And how about this? The other way.
4.
4, very good. It's the same logic. Now we come to 135 degrees. This, if I turn like this, 135-degree rotation. I'm waiting for your answer. So let us apply the logic. Okay. So suppose I put whatever I put here, the same color I put here. Right? Because otherwise it won't be fixed. Whatever I put here, the same color I put here. Whatever I put here, the same color I put here. Whatever I put here, the same color I put here. Whatever I put here, the same color I put here. Whatever I put here, the same color I put here. Whatever I put here, the same color I put here. So what does that mean?
Red and full blue.
Either, yes, complete it for me, please.
Full red or full blue.
Full red or full blue. So there's two choices. And similarly for the other, it's the same for the other one. Okay? Okay. Now let's come to the 180-degree rotation. So 180-degree rotation. So let me draw one more picture here. Okay, 180-degree rotation. So what is the logic now? Whatever I put here, I should put here, right? But then if I turn back, it comes back here. Okay?
Sir, we already done 180-degree.
Where did we do?
90-degree anti-clockwise.
90-degree clockwise is different from 180-degree clockwise. No? See, this is a different group element. This is a different group element.
Okay, sir.
Okay. See, you cannot deduce. See, for example, it is not so easy to deduce from the 45 what happens to the 90, what happens to the 180, etc. I don't think there is an easy, just because you did this doesn't mean you have done this. Let us just do this and see what we get. 180-degree rotation. So can somebody please answer this? There is a method in all this. And if you can see the method, you can answer you can do this very quickly. See, this logic is whatever I put here, the same I put here. Either if I put blue here, this is also blue. If I put red here, this is also red. That does not tell me what else I have, on the other ones. But these two are related. These two are related, and these two are related. So with that, can you give me the answer, please? So these two are a pair. I can choose them both to be red or both to be blue.
4C2.
You are on the right track, but tell me the right answer. So these two can either be red or blue.
And opposites are similarly.
These two can either be blue or red. Yeah.
Red or blue.
These two can either be these two and these two. So there are four choices to be made. Yes. The answer is
4C2.
Not 4C2.
16.
See, there are four choices.
16.
2 power 4. 16. 16 is the right answer. It's 2 power 4. Okay? So, okay. Let's do. Now, we are done with the rotations, right? So here, this is the identity. These are the 45 clockwise, anti-clockwise, 90-degree clockwise, anti-clockwise, 135 degrees clockwise, anti-clockwise, and 180 degrees, whether it's clockwise or anti-clockwise, is the same thing. That's 1, 2, 3, 4, 5, 6, 7, 8. That's 8 rotations. Let's do the reflections. Okay, so let me go back to this picture. So let us take a reflection, say, like this. Right, in this line. Okay. Now, if a diagram is fixed by this under this reflection, then what can you say? If I put some blue here, then that means when it gets reflected, it goes here. So whatever color I put here, I must put here. So these two are related. Now Can you apply the logic and tell me for
8.
these? 8. Why 8, sir? Why? What
Again,
was the logic for 8? Yeah.
if I'm selecting one bit,
This one?
just a bit.
Yeah.
Okay, if I'm selecting any one bit, there are two choices.
There is one choice. There are two choices for these two.
Any one bit. If I'm selecting the blue
you
or
can
red,
choose this. You can forget this and choose this.
yeah,
Right?
the two
There are
choices
two
for that
choices
one.
here. Yeah.
Again, for next one, two choices.
For these two are related. Whatever I put here, I must put here, so I can forget
choices.
Two choices.
Again, for the last one, two choices.
These two are two choices. Yeah.
Okay, and the point through which vertical line is passing is either red or blue.
That's two choices.
So again, there are two choices.
How about this?
Yeah, same color.
Same.
If
So what's the answer?
2 raised to power 4.
2 raised. I see 5 2s here.
But the top point and the bottom point.
No, it is the reflection through this.
Okay, correct. 2 raised to power 5.
2 raised to the power 5. Do you agree? Right. Okay, good. 2 raised to the power 5. Very good. That's correct. Okay. And suppose I take the line through this and reflection. What is the logic then? It is the same. You will get, it just changes. These two are the same. These two are the same. These two are the same. This by itself and this by itself. Again, you will get 2 power 5. Right. It does not matter which reflection I choose through the vertices. It's always 2 power 5. Do you, okay, I'll wait for that. Do you agree with that, or is that too fast?
Agree.
Agreed. Very good. But there are, let's see, but let's not rush. There are, let me draw another picture here. Okay. And there are these reflections like this, right? In a line like this. What about for these? So let me write into 4 here. This is for reflections through vertices, in lines through vertices. Reflections in lines through vertices. So there are 4 of those reflections, and each one of them contributes 32. What about these? Apply the same logic. It is the same logic.
2 raised to the power 4.
2 raised to the power 4. Very good. Now we can do this. Okay. Right. And there are 4 of them. The same logic applies to any one of them. Right. Okay. Now so let's do this now. Now we are close to getting the answer. So it's 1 over 16. So let me write in multiples of 16. So this is 16 times what? 2 power 4 is 16. So another 2 power 4 is left. Right? I'm writing it like that so that I can divide by 16. Right? I hope you understand. Right? So if I divide by 16, this will give me 16. Okay. I'll do that in the next step. Here, what do I have? 4, 8, 12, 16, correct? All these add up to 16. So that's another 16 plus this 2 power 4 is 16. Okay. Here, 2 power 4 is 16. So I can write it as 16 times 1, 2 is left out. So that is 8. And this is 16 into 4. So when I divide by 16, I get 16 plus 1 plus 1 plus 8 plus 4. I hope you are impressed with this calculation, which took us half a page, right? And I have not drawn a single necklace. right? Imagine having to draw 30 different necklaces and making sure that you have drawn all of them, and whether there are two of them are the same or not. So I hope you are convinced about the efficiency of doing it this way. Okay, so in the tutorial, we'll do it for the 7, for example. Okay, so number of necklaces with 7 beads. I urge you to do this, and maybe if 10 beads, some other large number, some large number. Take your favorite large number and try it for that. Okay. For example, you could take a prime number P, such as 23. Right? You can come up with answers. It will take you maybe 10 minutes to compute, maybe less once you are used to it. But so you see, now for large numbers like this, I can easily find the number. For example, for 20, the number is this. And you can find this number within a matter of 10 minutes. Whereas imagine drawing 27,000 odd necklaces. That will take years, right? Okay. Anyway, I hope you have, by this thing, seen the usefulness of this lemma. And the point I want to make here is the following. Now, in mathematics, we are often worried about proofs, right? Proofs are important, but even more than proofs, applications are important. So when you encounter a statement, it is nice to apply it, try to apply it and see what it actually means, to understand the content of the statement before trying to prove it. Okay, that's a general comment. So if you are teaching, you state a theorem, you don't have to rush to the proof. You can try to apply it first. Once the student has seen an application, then their appetite is whetted, hopefully, and they will be ready to see why the theorem is true. Okay. So let me now pass to the proof of this. So, but let me pause again and ask you if you have any questions. Yes, madam, go ahead.
So suppose we have 3 different colors.
Good question. So
Then
how do you do this? Well, the diagrams then will have 3 colors.
3 colors.
And you can apply the same method. So same method. Here, instead of 2 to the 8, what will you get here?
3 power 8.
3 power 8. And here, what will you get?
2.
No.
Oh, 3.
3. And so on. 3. Here. What do you get here? So let's see.
8.
Not 8. Why did we get 4? The 4 we got because it was, see, 90 means here these 4 are the same and these 4 are the same. So this 4 is actually 2 power 2. This 4 is also 2 power 2. That's the way it came. So these 4 have the same color and these 4 have the same color. Now, if you have 3 choices, what does this mean?
9.
9, exactly. So what you get for 3 beats, the answer will be 1 over 16 into 3 power 8 plus 3 plus 3 plus 3 square plus 3 square plus 3 plus 3 plus 3 power 4 plus 3 power 5 into 4 plus 3 power 4 into 4. Right, there you go. We did it in less than 30 seconds. Now you can compute this and come up with the answer. You see how beautiful the method is. The logic is the same, right? Many of them will fall. So, for example, if I look at this reflection, what does that tell me? These two are the same color. So, if I have three choices instead of 2, 2, 2, 2, 2 here, I'll get 3, 3, 3, 3, 3 here, which explains the instead of the 2 power 5, I've written 3 power 5. And it is the same for all the 4 reflections that pass through the vertices. Is that good, madam? Have I answered your question?
Yes, sir. Sir, but the 3 square, how will you calculate the 3 square? That is 90-degree rotation.
90-degree rotation is, okay, I'll draw the picture once again. Okay, let me draw this. Let's go through this once again. So what does 90-degree rotation mean? So whatever here, let's call it, suppose I have a red here. This should also be red, right? Because what are we computing? We are computing, looking at the possibilities of diagrams which are fixed when I rotate by 90 degrees. So when I rotate by 90 degrees, this bead will go here, right? But I must get back the same bead, same diagram. So, which means this should also be red. And when I rotate by 90 degrees, this goes here. But I should get back the same diagram. So this is also red. This is also red.
It's alternating color, red and blue. That is 3C.
No, don't think like that. Don't think alternating. See, it's better not to think like that. These 4 are the same color. That's what it means. If you put red, all 4 are red. If you put blue, all 4 are blue, right? So these 4, you can choose either blue or red, but that is one choice, right? If you put something, this is blue, then others also are red. And these four, let me draw a different, let me draw them in navigation. These 4 here, right? They are a set, so to speak, meaning if I choose one of them to be blue, the other 3 are also blue. If I choose one of them to be red, the other 3 are also red. You understand? So these 4 fall into one class and these 4 fall into another class. And each class gets a color independent. There are 2 choices. Okay. If we are doing 3 colors, then these 4 get one of those 3 colors. Let's say red, blue, and green. These 4 together can all be red, can all be blue, or can all be green. Okay. And these 4 independently can all be red, can all be blue, or can all be green. So that's 3 choices for this, and independently 3 choices for this. That's 3 cross 3, which is 3 square. Is that convincing, madam?
Okay, thank you.
Okay. No, if it is not convincing, you can think about it and ask me again later during the lecture or in the tutorial. Okay, I'm happy to return to this and explain. Okay. Okay. So with any number of colors, you can do this, right? If it is with p colors, then you will just get p to the 8 here, p plus p plus p square plus p square plus p plus p plus p power 4 plus p power 5 into 4 plus p power 4 into 4. You just compute it. So are you convinced that we can do this for any number of colors? Right? It is the same calculation. No difference.
Okay, thank you, sir.
Good. So this shows something in mathematics. See, suppose I asked you initially for the problem with, let's say, compute with n beads and where you can have m different colors, right? So what will you start thinking? We want to do it for m colors. So let's take 10 colors, say, and maybe you will try with 10 colors, right? And you will try. Now, so the point I want to make here is, suppose I'm given a problem. It is good to be have rather modest goals to begin with, right? Even if I want to solve the problem for any number of colors, 10 colors, 15 colors, right? It's good to ask myself, can I do it with just two colors? If I don't know the answer to two colors, there is no hope that I'm going to do with 15 colors, right? So even if you are asked for the question with, even if you are posed the question for some 15 colors, it's good to modify the question. In other words, what I'm saying is, when you encounter a difficult problem, you can modify the problem so that it becomes easier, right? You should not say, look, that is the problem I want to solve, and if I modify, it becomes easier, and that is not the problem I want to solve. The lesson is, if you try to make it easier, make it easier, make it easier, maybe the easier problem you can solve. And once you solve the easier problem, you will perhaps see a way of solving the harder problem as well. The point is, if you're not able to solve the easier problem, then there is no hope of you solving the harder problem, right? So, and this is something I find students don't often do. They're if you're posed a problem, they're stuck with it. They don't try to modify the problem. One of the important things that students should learn to do is ask questions of themselves, right? It is we somehow think that the teacher asks questions and the students answer, right? But any learning involves posing questions to oneself and answering them, right? Without that process, without that question and answering, I don't think most I don't think it's possible to learn. I would venture the statement that most of us learn by means of this asking questions and answering to ourselves. That question need not be asked by somebody else. I often find myself that I cannot understand something without asking questions and trying to answer them. Okay, they could be stupid questions, they could turn out to be difficult, they could turn out to be easy, it doesn't matter. But this process is very important. Okay. Okay, I will proceed to the proof of this theorem, but please feel free to interrupt me as always. Okay, I have one more comment before starting the proof. So, and it is this. Last time I was asked for some good reference, and I found this beautiful reference. I didn't know it last week, last Saturday when I lectured, I guess, but I know it now. This applied finite group actions, I found it on the net. It seems to be a very beautiful book by this gentleman called Adalbert Kerber. This is the title of the book, and it looks very nice, and it gives many applications of this orbit counting lemma and its variations to various other areas of mathematics and also to other fields of science, for example, to chemistry. Okay, so there are many important applications of this. So let me write it here: variations of the OCL, orbit counting lemma, have applications, have many applications. For example, to chemistry. And what I understand from this book is that historically it was these applications to chemistry that triggered the variations of this orbit counting lemma. Okay. So if you're, I mention this because students tend to ask what applications there are. And indeed, there are many, many applications, and they are discussed, for example, in this book. It's a very beautiful book. Okay. Now, proof of the orbit counting lemma. Now, the proof itself is also beautiful. So the statement is beautiful. The application we did, I hope you agree with me that it was, rather striking and beautiful. The proof also is very beautiful. Okay, so what does it consist of, this proof? Here, the main idea of the proof is the following. So what I do is I make a table, right? I make a table like this, right? You can apply this idea in other contexts. So this idea is a very beautiful idea. Okay, so here I'll write on, I make a matrix. The elements of the group are written here. So I have G0, let's say, is the identity element of the group, G1, G2, etc. The elements of the group are listed here. Let's call this G sub I. Okay. Okay. And I have various, so in this, so it's some finite group. And so here are the rows. Okay. The columns of the matrix are indexed by elements of X. So let's say X0 or X1. So let me, okay, maybe it's better to call this G1, G2, G3. Doesn't matter, but because let's not start counting with 0. Let's just count with starting with 1 as is the usual case, and so on, right? Let's say Xj is the general. Now, what I do is I have this, I put, so in this place, in every entry, so there are all these entries, right? I fill this matrix with 1 or 0. So I put here 1 or 0. Okay, and when do I put 1? 1 I put if Gi, this element of the group, right? Each row corresponds to an element of the group. Each column corresponds to an element of the set X. If Gi Xj is equal to Xj, I put 1. I put 0 if Gi Xj is not equal to Xj. So there are only two possibilities. Either Gi Xj equals Xj or Gi Xj not equal to Xj. In the first case, I put a 1. In the second case, I put a 0. Right? So I make this matrix. Is the matrix clear to everybody? Let me pause and ask.
It's clear, sir.
Clear, very good. So the idea now is I just want to sum the elements of the matrix. So how does it look? It's a matrix. There are some 0, 0, 0, 1, 0, 0, 1, somewhere 0. It's a matrix of, I'm just drawing some arbitrary, just illustrative thing. There are some ones here and there, right? In fact, if this is the identity, the first row will all be 1, right? Because identity fixes everything. I'm just trying to give you a feeling for this matrix. So the first row is all 1 because this is identity. If I choose the first element to be the identity, that is, you can, there is no need for that. You can, it can be the nth element, but one would think that it's natural to choose identity to be the first element. Okay. So the second element, there could be some zeros, some ones, etc. Okay. Now, here is the very simple idea. So what I can do is, I can, so tell me please, if I take the sum of all these, take the sum of all these. So when I take the sum of all this, what do I get here? What am I counting? I want you to answer. The answer is a certain notation. I want you to tell me what that notation is. So if I take G2, for example, where do I see a 1? Whenever it fixes an element, I see a 1. Right? Whenever it fixes an element, I see a 1. So when I add all these, I'm
The
just
orders
adding.
of x power g cardinality of the
Very good. It is x
G.
power g2,
G
right?
cardinality.
Right. Right. Here it is x power g1, and so on. Here in the ith place, it is x power g sub I. Correct? Okay, good. Let's do by column. So here, if I add this, what do I get? So what are these? Anytime there is a group element that fixes this given x, I count
Cardinality.
one. So what is this cardinality?
Stabilizer cardinality.
Very good. This is the cardinality of the stabilizer. Right? This is cardinality of the stabilizer exchange. Each column is indexed by a certain set element, and the column sum, the sum of the elements of that column, is the cardinality of the stabilizer. Okay. Now it's obvious that if I add all these column sums, if I put plus 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 and I get some answer, that is the same thing if I add all the rows, right? Because both of them will give me the sum of all elements. You agree? Because whether I see, if I sum all these ones and then sum these numbers, that is the same thing as sum all these row-wise sums and then take the sum row-wise all these numbers. So you will get here the sum of the elements of the matrix. Okay, I guess that is obvious. I hope you agree with me. So what can I write? I can write the sum over all columns x in x of the stabilizer gx is equal to the sum over all elements g in g this is what I get from this. Do you agree?
So,
Yeah, it's a beautiful way, no? It said, see, this is a very simple idea. You make a matrix of zeros and ones, and which has some meaning because the row sums have some meaning, the column sums have some meaning, and you just use the obvious idea that the row sums must be equal to the column sums. Right? And look, already here, this is starting to look like the right-hand side of my lemma, right? So I'm missing a 1 over square order of g. So this we have proved. This we have proved by just looking at this matrix. This matrix tells me that this equality is true. Okay. Now let me divide by the order of g on both sides. So what do I get? Here x is in x. I divide by the order of g. And I keep it. So I've just divided by the order of g on both sides. Here I have even taken it inside the sum. Here I've kept it outside the sum because here this is how it appears this is my right hand side of the lemma. So let me use a different. This is RHS of the lemma. So I'm almost there. I have gotten the RHS. What is the left hand side of the lemma? What should this be in the lemma? So the question is this equal to the number of orbits? If I can show that it is the number of orbits, the lemma is proved because I'll get number of orbits equal to the right hand side what the lemma claimed. Let me pause here and ask if you have any doubts, any questions. I need some feedback, otherwise I'm lost. Am I making sense? Or should I explain again? Or it's all okay and we can go forward? I need some feedback.
Clear, sir.
Clear. Okay, good. Okay. Now let me ask you, how do I show that this is the set of all, this is the number of orbits? Okay. So this is what we are doing. That's all that remains to be done, right? This is proof of this. Okay. Let's do it here. I'll go back to color. Okay. Now, recall that we had this equality, right? G by the stabilizer equal to Gx, like this, right? It is the cardinality of the orbit of X. Correct? Remember this. So recall. We had this because we had this lemma that G by Gx, the coset space G by Gx, was isomorphic as a G set to Gx. Right? Let me write it in a different font here. Is G by Gx is isomorphic to this Gx as a G set. And what was the isomorphism? Gx, the coset, this coset maps to G times X. So this was an isomorphism of G sets. In particular, it's an isomorphism of sets. In particular, the cardinalities of these two are the same, and that's how we got this. We use this, remember, to deduce that the centralizer, the cardinality of the centralizer of an element in a finite group, and the conjugacy class of that element, the cardinality of the conjugacy class, these two, when I multiply them, they are reciprocal in the sense that when I multiply them, I get the order of the group. Okay, we had used that. Okay, now I substitute that here. Now what does this give me? This is G sub X. Okay, this is G sub X. So if I use this, this becomes summation over X in X 1 over the cardinality of the orbit of X. So you have to pay close attention here. This is a G sub X, and this is G X, the orbit of X. This is the orbit of X. So they look the same, look very close to each other. So if you're not paying attention, then it can cause confusion. So here too, this is G sub X, and this is the orbit of X. Okay. So if you don't like this, you could use orbit of X, some notation like this. Okay. I'm fond of this notation, although it can cause this confusion. I'm used to this, but if you don't like it, if you think it is too risky, then you can change this. You can denote by some other symbol the orbit of X. Okay. Now here is another simple idea, right? I want to claim that this is obvious. I'm claiming that this is obvious. This is equal to the number of orbits. And once I claim that, I'm done, because the number of orbits is equal to this number. And that we have seen because of this equals this number. And by this matrix summation, we saw that the number of this equality holds. And indeed, I have the right side here. So all it requires is to observe that this summation here is the number of orbits. And that is again a beautiful, I don't have to write anything. I just have to draw a picture to convince you that this is true. And this is how we I'll convince you now that this equality holds. How do I do this? So observe the following. Let's draw a picture, schematic picture. So this represents X, and these are the various orbits of X. Okay. I have to count the total number of orbits. So in this example, for example, let me put one more here. 1, 2, 3, 4, 5, 6, 7. That would be each partition represents a each partition represents an orbit. Okay, very good. So now let me use these dots here as elements of X. Right? It's very convenient to have these dots. This application gives me these dots. So these are elements of X. Let's say this is just a schematic picture, but it is very nice to apply this. This has a single dot. This has 3 dots. This has 5 dots. Or 6 dots maybe. Okay, right? Okay. Now, what am I doing? I'm counting over all elements of X. But what am I counting? 1 over the cardinality of the orbit of X. So I'm summing over the entire set X. But what am I summing? For each X in X, I count 1 over the orbit. So this point, there are 6 elements in this orbit. So the weight attached to this is 1 over 6. Here it is 1 over 6. Here it is 1 over 6. Here it's 1 over 6. Whereas if I take here, what is the weight attached to this? Anybody? It is 1, because it's 1 over the cardinality of the orbit of X. So please tell me what is attached to this point here. I'll use a different color. What is the weight attached? I'm calling this the weight attached to the element, just for the sake of explanation. So
1 by 3, 1 by 3, 1 by
1 by
3.
3, 1 by 3, right? Each one of them is 1 by 3. Very good. What is the weight attached to these? I'll use a different color once again. Here.
1 by 4.
1 by 4. Very good. These all combine with 1 by 4. How many, what are the weights of these? So let's count. 4, 3, 7, 8, plus 2, 10. So each one of these comes with
1 upon 10.
1 upon 10.
1 upon 10.
Right. Each one of them has weight 1 upon 10. And each one of these has 1 upon 5. Right. Let me use some other color. And maybe you cannot see that, but it doesn't matter. And each one of these has, let's count again, 1 over 9. 4 plus 3 plus 2. Right. Now, if I sum all of these, okay, let me use the black color here. If I sum all these inside this, how many points are there? 10 points, right? That's why I put 1 over 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And each point comes with weight 1 over 10. So when I sum this, what do I get?
1.
Okay, very good. When I sum all of these, what do I get?
7.
No, not 7. It's 1 by 6, 1 by 6.
No, 1.
1. So all these sums to 1. All these sum to 1. When I sum all of these, what do I get?
Again 1.
When I sum all of these, what do I get?
1.
1. So for each orbit, I get 1. So what do I get here? 1, 2, 3, 4, 5, 6, 7. That's the number of orbits. So for each orbit, so when I sum this, for each orbit, the summation over each orbit, for each orbit, we get 1 as its contribution. So what, if you want, you can more formally write this as, instead of X in X, 1 over the orbit of X, cardinality of the orbit of X. This you can write where, over all orbits. Okay, O is an orbit. So orbits O, sigma, X in O, X in that orbit, 1 over cardinality of O. Right? This is what this is. Instead of, so I am summing over these. So these O's represent, there are 6 O's here. 1, 2, 3, 4, 6 or 7. 7. 1, 2, 3, 4, 5, 6, 7. Right? 7 different orbits. For each orbit, this is, I'm summing over this orbit, for example, or this orbit, and 1 over the weightage. The weight given is 1 over the cardinal. So this, what is this? This is, you can bring this out of the summation sign, and x is in O. That, so this is 1. Do you agree? This is 1 for no matter which orbit I take. That's what we have observed, because there are 9 points here and each one is given weight 1 over 9. 10 points here and each one is given 1 over 10. Right? This is 1, and therefore this is summation over orbits, and 1 for each orbit, which is just nothing but the number of orbits. Each over each orbit, the sum amounts to 1, which gives you contribution of 1. So when I take the sum, I must get the number of orbits. Okay? Is that convincing enough? Or if you have any questions, I can explain again. I'll wait for your response.
Yes.
Okay, good. So you can think about it again and ask me in the tutorial or at the end of the class, whenever. Okay. So if you are seeing it for the first time, it requires some, mathematics often needs us to reflect on it, go back, think about it, meditate upon it. Only then do we start begin to understand. So here, so what have we done? Let me summarize what we have done. We have stated the orbit counting lemma and applied it to solve our necklace problem, which we had introduced as a motivating problem. Okay, and then we have observed that there are many other applications of the orbit counting lemma, or maybe more properly, it's the variations of the orbit counting lemma. And we noted that this is a reference. Okay, and then we went to the proof of the orbit counting lemma, and now that proof involves two beautiful ideas. One is this making of a matrix like this, and just observing that you take the rows, you do the same summation in 2 different ways. If you do it by first taking the row sums and adding them versus taking the column sums and adding them, you get, of course, this equality is obvious. If I do it this way or if I do it this way, I must get the same answer. So this equality is obvious. But then if I look at the left-hand side and look at the right-hand side, I get 2 things for which I have given meaning, which I can interpret. And then if I use this other fundamental thing that we have observed, right? And finally, this very simple and beautiful observation, the proof is done. So indeed, the proof of the lemma is itself beautiful and quite simple at the end of the day. Okay. Now, in the remaining few minutes, let me go on to explain some other simple and very fundamental applications of group actions. Okay, so let us look at, so let me just consult my notes for a minute and see if I have any preferred way of doing it. Okay, let's do this. So once again, G acts on X. G is a group, X is a set. The structure of X. So recall that I made the provocative statement that, so recall. recall that G acting on the coset G mod H, right, where H is a subgroup, is the most important action. So let me put that in red. So when somebody says that it is you get irritated and say, why is it the most important action? Well, I will explain in what sense it is the most important action. So here it is. Okay, so let us draw this picture again. G acts on X. And here I have, once again, this is, I'll draw this picture again and again. So this is the picture of the orbits of X. This is a picture of the orbits of X. And the orbits are equivalence classes. And equivalence classes form a partition of, if you have a set on which you have an equivalence relation, then the set gets partitioned into equivalence classes. So what I have is X is equal to here union of orbits. Disjoint. So this means disjoint union. Okay, that is obvious because the orbits form an equivalence class. Orbits are the equivalence classes of a certain equivalence relation, namely the orbit equivalence relation, which we had introduced. So this is obvious, right? So we have a partition. Okay. Now, observe the following. Each of these, each orbit is an invariant set, is a G, okay, or G stable, that's another word we had used, is a G stable set. In fact, we had observed that invariant subsets, so let's recall what a G stable set is. A subset X prime of X is G stable. This is the definition. I'm recalling it. If for G in G and X in X prime in X prime. So here you should add any. It is understood, but I'm adding that for emphasis. For any G in G and any X prime in X prime, we have Gx prime. So if I take an element of the subset and act it by an element of the group, it belongs to the subset. It doesn't go out. That's the meaning. Okay. And an orbit by definition is stable because by definition, it means that when I take an element here and act an element of G on it, I get another element in the orbit, right? Okay. But how does this look? Well, this G, so each of these is an invariant subset, a G stable subset. Each orbit is a G stable subset. So in order to understand, so so to understand how G acts on X, we can break up G into orbits, break up X into orbits, sorry, break up X into orbits and understand the action on each orbit separately. But now here is the final statement. But if you have a single orbit, but when you have a single orbit, Okay. Then G, we can use this relation. This orbit, this single orbit is as a G set. This is a G set, which means the action of G on it can be understood as the action of G on this coset space. So in this sense, this action is the most important. So if I understand the action of G on cosets, then I've understood the action on G of G on any set X, because I can break X up into orbits, and then I can understand the action on each single orbit as the action on a certain coset space of the subgroup. So put H equal to G sub X, the stabilizer at X, and look at the action of G on G mod H. Then you've understood the action on this orbit, and do it for every orbit and put them together. Okay, so at least philosophically, it is clear that if I understand the action of G on every G mod H, I have understood the action of G on any set X, because it clearly, the action breaks up into pieces which I can understand in terms of the action of G on the cosets. Okay. Now, here are some applications of this. The application of the idea that you can break this up into orbits. Okay. It's a very simple idea, but once again, these simple ideas can give surprisingly beautiful applications. So, applications that are not so simple or not so obvious. Okay. So let's write this. X is equal to the number of orbits. You can also implies this is X is the disjoint union of orbits. This means the cardinality of X is equal to the sum of the cardinality of various orbits as I vary over. So let me write here cardinality of O as O varies over orbits. This just means the trivial statement that if I want to find the cardinality of this X, I look at the cardinality of this, plus the cardinality of this, plus the cardinality of this, and so on. Right? It is that trivial statement. It appears that I'm not doing anything much here. But here comes the surprising application of this, and here it is. Okay, suppose G is a P group. Which means that is, so the notation means P is a prime. G is finite, and order of G is a power of P. Okay. Then you can write this X. Okay, let's write this. You can rewrite this. Actually, let me rewrite this even before this. This also implies. So let's look at this picture again. And maybe there are some singleton orbits. Let's say there are some singleton orbits here. There is a single point here, and maybe there is this singleton orbit here and so on. Now, what does it mean to have a singleton orbit? It means that that point is fixed by all elements of the group, right? So separating out the singleton orbits themselves, I can write this like this. So X upper G plus O non-singleton. So let me explain this. X upper G is the set of all, by definition, it is the set of all X in X, such that Gx equal to X for all G in G. So clearly, these elements form singleton orbits. Each of them is a single orbit. So I can sum all of them. So that 1, 1, 1, 1 that I get so many times. So instead of writing 1 plus 1 plus 1 so many times, let me write like this. Right? So this summation takes care of all singleton orbits, and this summation is all non-singleton orbits. Okay? But now observe that O divides the order of the group. So this divides order of the group. So this divides G. So, and if this is, because we have seen the cardinality of any orbit divides the order of the group, right? We had used this to say that the order of any conjugacy class divides the order of the group. Okay. Now, when G is a P group, this means, so this cardinality divides a prime power. What are the divisors of a prime power? There are other powers of P, or of course, 1 is also a power. But if I have taken non-singleton orbits, this cannot be 1. Therefore, these numbers are divisible by P. So what I get finally is that X is so if a G, so the statement is, if a G is a P group acting on a finite set X, then the cardinality of X is congruent modulo P to the set of fixed points. And the proof is what we have done. It's rather easy once you know that the orbit order of any orbit divides the order of the group, because I have chosen these to be non-singleton. I have arranged such that these are all non-singleton. And whenever I have a non-singleton orbit, its order divides the order of G. So it must be a power of P, and it cannot be 1 because it's non-singleton, which means it is P or P square or P cubed or something like this, which is all divisible by P. So each one of these is divisible by P. So when I can, this is all 0 modulo P. So I get this equation. And this has many applications. For example, so can apply this to prove Silo theorems. And how to do this is explained in the second unit of my notes. We are unable to cover it in my lectures, but you are welcome to read it, and maybe sometime you will explore this. Okay, so let me stop here, and that finishes my set of lectures. I hope you enjoyed them. This Saturday, I'll have a tutorial. Your questions, if any comments, are most welcome. If you have long-term questions, I am happy to answer them also by email. Thank you very much for your attention. I really appreciate this opportunity to speak, and I thank Mepco, Professor Radha Jayalakshmi, Professor Gurusamy, and others of Mepco, all their colleagues, for this opportunity. Thank you very much.
Thank you, sir. Thank you so much, sir.
Thank you, sir. Thank you so much.
I'm happy to answer questions as usual.
Okay.
Okay, sir.
So there is some chat. Let me see if there is any. Oh, it's only thank you. Okay, thank you. I really appreciate it. So there was a, can you explain again? I didn't notice that because I cannot see the chat as I'm sharing. Sorry about that, Ganesh, Mr. Ganesh. If I have not explained it, could you can ask and I'll explain.
No, sir, you explained it again. Thank you.
Okay, thank you. Thank you. Yeah. Questions, comments are welcome. Yes. Go ahead,
In
madam.
necklace problem, we use in necklace problems, so we use 8 bits. Suppose it is suppose 9. We have reflections that is x power g in reflection x power g only.
So just 1 second, madam. Your voice is breaking, so could you come closer to the microphone, maybe? So you want to do with 9 beads? Is that what you want to do?
Suppose, in 9 bits x power g, modulus of x power g.
Yeah, okay. You want me to write? So you want to do with 9 beads? Okay, I understand. How many color beads? Just 2 colors, blue and red, or more colors? 2 colors.
Sir.
Okay, very good. Okay, let's do that. Yeah, we can do that. Yes.
In reflection, we have only not using the two beats. It has only 1 beat and opposite sides.
Yeah, okay. Let's understand.
Reflections.
Can I start sharing again? Let's do 9 beads, right? Yeah, by the way, the lecture is over, so formally over. Please, those of you who have to leave, may please feel free to do so. I am just answering. I am happy, however, to remain for a few minutes and answer your questions. So those of us who have the time can stay, but those of us who have other work to do, feel free to leave. Okay, I'll start sharing again. Is that okay, madam?
Yes, sir.
Okay, I'll start sharing so I can try to explain this. Okay, so we are doing for 9 beads, right?
Your screen is not visible, sir.
Oh, okay. My screen is not visible. Thank you for now. It should be.
Yes, sir.
Okay. So 9 beads. So your question was, suppose I take a reflection. So let me try to draw 9 beads. It's a little difficult to draw 9 beads. Let me see. So these two, my picture may not be great, but I hope you will pardon me for that. Something like this, right? So
Okay.
the reflection will go like this. Right?
Yes, sir.
Okay. So yeah, what is your question, madam?
So in that case, we have only 2 power 1 for 2 power 4 about reflection in 2 power 4 and
No, not 2 power 4.
2.
Not 2
2.
power. So this
2 power 5.
2 power 5. Very good. 2 power 5 for every reflection. And
reflections.
And there are how many reflections? So you can do for each reflection. There are 9 reflections. So you will get this for the 9 reflections.
Okay.
So your calculation will be like this: 1 over 18, right? And for identity,
2 power 9.
2 power 9.
2
Okay,
power
plus
9.
2 power 9. Yes, I have written that. And for the rotations, what will I get for this rotation?
40.
Not 45, whatever it is. 360 by 9.
40 degree. Okay, sir.
Okay,
2,
whatever.
2.
Yeah. 2, right. Okay. And the same for the other way, right?
2.
Yeah, 2. Okay, so this is for, okay, is it okay if I write 2 here? Okay. And
Yes,
how much for this, for this rotation?
80.
So the logic for that is whatever is here is also here, that is also here, that is also here, that is also here. You see how am I going? I'm going by jumps of 2, which is also here, which is also here, which is also here, which is also here. So everything is the same. So that is also 2, right? Okay. And similarly, this is also 2.
Yes.
Right? Now let us look at this rotation.
Okay.
So that means, let me use a different color now. Whatever is here is here. Right? I go in steps of 3. Whatever is here is here. So these 3 are the same color. Similarly, these 3 are the same color. And similarly, these 3 are the same color. So I have 3 choices. For these 3, I choose one color. Independently, for these 3, I choose one color. Independently, for these 3, I choose one color. When I say one color, I mean you can choose the same color for these 3 as well as for these 3. So this is how many? 2 power? 2 power 3. Very good. Plus 2 power 3. And the same thing for this as well. Right?
Yes.
That's another 2 power 3. And what remains is this one. Let's do for this rotation. So let me draw a different picture here. I hope I do this correctly. Okay, my picture may not be great, but I hope you understand, right? So we are doing for this rotation. So let's start. Whatever is here is here. So I go by steps of 4. 1, 2, 3, 4. Whatever is here, 1, 2, 3, 4 is here, correct?
2.
And then whatever is here is 1, 2, 3, 4 is here.
So 2 colors.
Just 2 colors. Very good. Very good. Let's just do it. Correct. The answer is correct. Very good. 3, 4. Whatever is here is here. And whatever is here is 1, 2, 3, 4 is here. Whatever is here is 1, 2, 3, 4 is here. 1, 2 is here. And that same thing is here. Something I may be mistaking. Okay, let's do this again. Whatever is here is here. That is 1, 2, 3, 4. Right. And this is 1, 2, 3, 4. And from here 4. 1, 2, 3, 4. And from here 1, 2, 3, 4. And from here 4 steps. 1, 2, 3, 4. And from here 4 steps. 1, 2, 3, 4. Am I making some mistake? One. Okay. From here. Here I was making a mistake. From here I go 4 steps, I get here. And from here I go 4 steps, I get here. So everything is the same. So the answer is 2, right? So for this it is 2, and for similarly for this also it is 2 by the same logic. So there you go. We have the answer here.
Thank you.
So 1, 2, 3, 4, 5, 6, 7, 8, 9. These are the 9 rotations. And these are the 9 reflections. Okay, you can easily write down the answer. Is this good?
Okay.
Welcome. Okay, any other questions? Feel free to also, switch on your video if you feel like it, by all means. Once again, I thank you, Dr. Guruswamy and Dr. Radha Jalakshmi and everybody for this opportunity to interact with teachers. Thank you for the invitation.
Sir, thank you, sir. Thank you for accepting
Okay,
our
sir.
invitation,
Thank you, sir. Thank you for your wonderful lecture, sir.
It's my pleasure. So if there are no more questions, we can call it a day, but I'm happy to answer questions if there are any, or listen to comments, or if you have general queries also, I'm happy to address them. Okay, maybe we should call it a day.
Okay, sir.
Because I don't hear any questions. So I'll send you the notes as usual
Okay, sir.
immediately, and I will also send you the tutorial sheet. I'll send it immediately so that people can start looking at it,
Okay, sir.
and then we'll have the tutorial on Saturday.
Okay, sir.
Okay, sir.
I
See
will
you on
just check.
Saturday, sir.
I will just check with the other speakers.
Okay.
It may be a good idea for the if they want to have a tutorial. I can do tutorial later on a later Sunday,
Okay, sir.
because that will give people a little more time to try the problems. We'll see how it works. But I'll send the tutorial sheet and the notes immediately.
Okay, sir.
Okay, sir.
Bye.
Thank
Thank
you.
you. Thank you.
Thank you,
Thank you,
sir.
sir. Thank you so much.